Welcome back to the ETSI IQC Quantum Safe Cryptography Virtual Executive Conference. It's time now for our panel discussion on the challenges of moving to quantum safe technologies. Now, quantum safe cryptographic algorithms have different bandwidth and computing requirements than traditional cryptographic methods. So how will this impact the performance or reliability of today's communication systems? And when should we start this migration? And how can we avoid any resulting negative performance and reliability issues? Well, to address these questions, let me introduce our guests. Brian Lamarkia, Distinguished Engineer at Microsoft. Panos Kampanakis, Product Manager at Cisco Systems. Matt Campagna, Senior Principal Engineer at Amazon Web Services. And Jaya Balu, CISO at Avast Software. Welcome, everyone.
Thank you.
Now, quantum computing impacts the security of the algorithms we use today for digital signatures and key agreement and public key encryption. Matt, I'd like to ask this of you first. How do you order or think about the order in regards to the time sensitivity of replacing these algorithms with quantum safe alternatives?
We see the long-lasting requirements of confidentiality as the most time sensitive when it comes to rolling out a quantum safe or post-quantum solution. We don't know the precise sensitivity of all of our customers' data, so we model that sensitivity based on our most sensitive customers. And for them, they look at 30-year timelines for the security of their information. So we see that there's a reason to start preparing our infrastructure now so that when standard post-quantum schemes are available, we can roll them out as quickly as possible to secure that data for the future.
Thanks, Matt. Anybody else want to share their views about how we go about this ordering of replacing the existing algorithms with quantum safe ones?
We have an extra use case for us. That, what Matt said, we agree confidentiality is very important, but we also have a use case for signatures in hardware that lives for a very long time. These signatures are used for image signing, and this hardware that lives in critical infrastructure for decades, we have realized that that's an urgent use case for us too, right? Instead of waiting for another 10 years. The migration is more urgent in this use case. So I think that's an extra important aspect of it for us, at least.
So I think, as I agree with Matt, that we're going to focus on confidentiality and upgrading our encryption algorithms first, because we have to provide our customers with defenses against what we call record now, exploit later. That is, we have to assume that our adversaries that can see encrypted network traffic are going to record that for later exploitation when quantum computers of sufficient size become available. But Panos' point on signatures is also very important. When you think about the infrastructure needed to do automatic security updates for hardware and software and systems, you have to make sure that you have deployed quantum safe signature verification into your devices before a quantum computer becomes available that could mimic or forge digital signatures based on classic algorithms. So both parts are important, but the initial focus on the encryption technology and the encryption uses is we see that too.
Chair?
I want to say that I very much agree with my fellow colleagues, but I do think that there's a fundamental notion of what Panos brought out, which is that actually you have a very long-term requirement to continuously update firmware. And it's not just critical infrastructure that use these kind of devices, but there's a lot of IoT implementations where the device gets deployed and then exists out there in the wild for the foreseeable future. So I think there is a very strong use case for not just critical infrastructure, but the larger IoT space to also have the signature verification. And I would just argue that we should be starting earlier no matter what with all of these things.
Yeah, good point. Thank you. I'd like to move on to looking at the work that NIST has been doing. NIST has announced round 3 finalists and alternative candidates. From the finalists selection, do you see schemes that will be beneficial to your early adoption use cases? Panos, perhaps I could come to you on this one first.
Yeah, sure. So we and industry peers, like my colleagues here and other industry peers, have done some testing with the NIST candidates. So I think we and my colleagues would agree with me. There are NIST algorithms that look satisfactory for most of the use cases. So for chems, I think the finalists will perform decent in most of the live protocols, as we call them, TLS, DTLS, SSH, etc. So we have done testing with Entru and Kyber, but I think Sabre is in that same category in terms of performance. And then for signatures, in our testing, we have seen the lattice-based finalists perform well. Dilithium, I think, is a good candidate. Falcon is a little worse because its signing is slower. And then the multivariate scheme, the rainbow scheme, could have some use cases for signatures that do not transfer public keys. That could be the case for other algorithms that have big public keys but small signatures. And then I think finally, from what we have seen and what we want to do at least, we have a very strong use case for hash-based signatures to be used for software upgrades and image signing and secure boot. We trust these signatures enough, to migrate to them, and they're not so new. They have been well studied. So image signing for these signatures is a good use case, and they perform okay as well. So these are the more prevalent algorithms that I see, being useful, at least from the get-go, as a swap and replace. But of course, that also depends on what NIST standardizes, right? So if NIST standardizes one or the other, then we'll have to adjust.
Anybody else got any comments about promising candidates for early use cases, or is it a case of, we have to wait and see what NIST actually does standardize? Brian?
Yeah, so first off, I should admit that I am not unbiased in this, as my team and I are co-submitters on 3 of the algorithms that are in the alternate bucket in round 3 and may be eligible for standardization in round 4. NIST has committed to picking a ring lattice scheme out of the 3 that they chose as finalists for round 3 for encryption, and one of the 2 signature schemes. And whatever they pick out of that is certainly going to be good enough for a large number of cases, and is something that you can start testing with early. You can start testing with that now, and you can start to detect whether or not your systems are sufficiently cryptographically agile. And certainly by the time NIST standardizes one of those. Guidance from NIST is going to be really important here, because if they do as they have indicated and have a further round 4 for some of the newer schemes that are in the alternate bucket, and they've implied they're going to do that, those may be targeted to particular use cases that may be more appropriate for particular cases. I would suggest not necessarily waiting unless you've got only one opportunity in, say, a 15 years to update a critical infrastructure, but actually starting with the schemes that are going to be available from round 3 to test your cryptographic agility, to test your system's ability to just run with any post-quantum algorithm, period. And then you can look at sort of what comes out of round 4, whether it's more appropriate for your particular situation. There are cases where we believe there are use cases where we're really going to care about short public key size, and where some of our schemes actually are better fit than some of the ones that are in round 3. But that's going to really depend upon the use case. And so good, clear guidance from the community, from NIST, and from all of us who work on these algorithms and protocols as to what's the best fit for where is going to be really important as we face this migration.
Thanks, Brian. I'd like to just jump in with a question, because we are putting this out to our audience, and we're hoping to get a lot of questions in from our audience to you. But I'm sure one of the questions is going to be at what point do I, as a company, jump in? At what point do I commit, or how long do I wait for this process to continue? Matt, I just wonder if I could ask that, because I'm pretty sure that's going to be one of the questions we're going to be getting from the audience. As when do I move? How soon is soon?
Well, I think we're seeing customers wanting to understand what the impact is going to be to their applications today. So what we've done is we're in our second year of deployment of postquantum TLS using our open source implementation, and so we've moved that into production web services like AWS Key Management Service, and that library is also integrated into developer previews of our client-side SDKs. So customers can understand the impact of what those post-quantum connections will have in their applications, and they can begin planning for how they might need to modify either the performance requirements or some other infrastructure aspect that enables them to leverage the connection for a longer period. To date, we've put Pike and Psych, and we've recently integrated one of the round 3 candidates, Kyber, into that TLS implementation. So we're hoping by these experiments that companies are doing, like our post-quantum TLS, like the Open Quantum Safe project at the University of Waterloo, that will enable people to start experimenting with these tools to get a sense of the impact to their applications and infrastructure. So I would say now is a good time to start.
Now is a good time. Well, thanks for that, Matt. And it's another reminder to our audience to please send in your questions to our guests, because we are eager to hear from you. Let me move on to some projects and experiments that we might have underway. Brian, let me ask you, are there any public-facing post-quantum projects or experiments that you've done or started to date?
Yes, thank you. And actually, there are a few. Matt mentioned the Open Quantum Safe project at the University of Waterloo, to which Amazon contributes and my own team contributes. And through that effort, we have participated in integrations of a large number of post-quantum algorithms into OpenSSL and OpenSSH and OpenVPN. And we've been doing testing with those, looking at the performance of post-quantum algorithms on those protocols. The OpenVPN work started as a way for us to secure connections from, say, a laptop up to the edge of the Azure cloud. And we've done a couple of then public experiments beyond that. The one most recently you may have read about, the team that sits next to me at Microsoft Research does research on submerged data centers, underwater data centers. And for 2 years, we've had a shipping container-sized pressure vessel submerged off the north coast of Scotland with over 850 Azure servers in it, connected by one big fat power and Ethernet cable to the shore. We've been running a post-quantum encrypted network tunnel from our labs in Redmond, Washington in the US, all the way over to Scotland and securing the network traffic over that and measuring the performance characteristics of post-quantum algorithms over an encrypted network tunnel. And so we've actually, that project just ended because the container reached the end of its submersive period and it's now out of the water. And we're looking at the data along with the performance of those servers.
Did you find it an invaluable exercise?
It's been valuable for us on the post. So for the server folks, they actually found, I'll just throw this interesting fact out, that server failure rates inside the pressure vessel were only 1/8 of what they are on land. They suspect that's because they actually pressurized the vessel with nitrogen and that it helped the failure rate decrease. For us, what it did was it validated our lab testing of the performance characteristics of the post-quantum algorithm, and it showed it is completely reasonable to roll these algorithms out in conjunction with what we're using today to provide an extra level of security. There's a slight performance hit that you take when you set up the connection, but since encrypted network tunnels are long-lived connections, that cost is completely amortized over the long life of the connection. So yeah, we got a lot of valuable data out of that experiment, and we're thinking about what we're going to do next.
Excellent. Anybody else, any other guests have got some examples? Oh, Jaya.
Yeah, so one of the things that we did when I was at KPN is that we tried to figure out what it would look like if we set up a post-quantum VPN and then specifically over a WireGuard implementation, and that we could then distribute that as a VPN for our customer uses. And there's some interesting dynamics in terms of optimization for bandwidth connections that are just regular bandwidth connections. And I find that this stuff is for us more than just something interesting that it is to play with, that it's actually a commercial business case where we're actually gearing up to provide this for the future. And that went well, and it was with Crystals and Kyber, so I'm hoping that they still make it to round 4, so the work that we did will not be a waste.
Excellent. Thank you very much. Matt, back to you.
So as I mentioned, we've been focused on TLS and getting that into as close of a production wide-scale use as possible to collect data, to understand, is it ready for wide-scale deployment, or do we need to sort of better tune our networks or better modify our protocols? So far to date, the results from Kyber and our integration are very promising. And that looks to be something that we can use that round 3 candidate for larger scale deployments to get a sense of its suitability for sort of being the default option in a hybrid mode.
Great, thanks. Now, quantum computing is in its infancy. We understand this, but I wonder, what confidence do you have that we will not see the development of new fundamental quantum algorithms that apply to coding problems and cryptography? How does this cause you to view crypto agility in a new or more critical way? And if so, what steps are you taking to build any additional agility? Jaya, could I ask you first of all about that?
Well, I think crypto agility is there because you're worried that one algorithm won't cut it for the foreseeable future, and therefore you're going to replace it with another algorithm that will. So you have to be agile in order to transition from the one algorithm to the other. In all fairness, confidence in a particular cryptographic algorithm is something that's established over the length of time that it's been used, so that you have a sort of ability to ascertain that it hasn't been broken, that it's still a viable algorithm. And there are no guarantees, but I think that's something that's going to just be established over time. And the work that is being done around figuring out how to actually break some of these algorithms, that's work that started ever since we had McLeese back in the 1970s. So I really believe this is a test of time, of not too much else. And there's no guarantee that we're going to break any of the algorithms with classical computers. So it's first establishing that we have a viable quantum computer, and then looking for other challenges to ascertain confidence in those algorithms.
Great. And Matt, what do you think about this?
Well, I'm certainly no expert in quantum computing or quantum algorithms. I do try to track what those experts are saying. But I'm also weighing that against what I'm not seeing, and that is the computer scientists that are coming out of post-secondary education programs and our universities. They don't have real experience in quantum algorithms. And it's safe to say that, like, as a community of computer scientists, we're sort of at our infancy in understanding what we can harness from quantum computing and the types of quantum algorithms. And that directly impacts how much assurance we should have that any of the schemes are going to be safe against large-scale quantum computing. So I see two things that can help combat this uncertainty, and that's the agility and redundancy. So the investments we are making now is to be able to continuously improve or take the latest NIST schemes and eventually their standardization and use them in a hybrid way, or a double sort of tunnel of the communication channels, to have both agility and redundancy to protect against that uncertainty.
Thanks. Panos, have you got any thoughts about this agility and redundancy?
Yeah, sure. I agree on the points that we don't know what's going to come out as more experts come out in this space in quantum algorithms and the agility aspects. I think the post-quantum algorithms are a little unique in terms of agility, and the reason being is that traditionally what we were used to is, we've had Diffie-Hellman, and then easy Diffie-Hellman came out. So it was more or less an exponentiation on either side. The exponentiation was done differently over curves or over prime fields. But now with these new algorithms, we have encapsulation and decapsulation. And these operations are not exactly the same like we were used to before. So I'm saying, in terms of agility, our job is a little harder now swapping, because we can't really swap because the algorithms are not behaving, the primitives are not behaving exactly the same. So, agility has been a battle, and I think we'll keep fighting it. I don't think we can be perfect, but we can do the best job that we can in order to be able to change and evolve, like Matt said, and Jay.
Yeah, no, I wanted to make the point that it's true that we don't have a large professional group of people coming out of universities with a strong background. I mean, even professional cryptographers. There are people who work in cryptography who are not still to this day very comfortable with isogenies, and these are people who I work with, who I'm completely relying on their knowledge to help us figure out, which way to go with a particular primitive, and they're not that comfortable with some of the work that's being done on isogenies. So I think that there's a certain amount of trying it out, just allowing a certain amount of tolerance for failure when we initially start, and understanding that it's going to be indeed a process that begs the question of how can we operate on the principles of defense in depth. So assume that something will fail, but then build that redundancy indeed, or resilience, in order to be able to do something else about it. So whether that's indeed simply the hybridization, so using multiple algorithms, or agility, or building in a secondary, completely different aspect for doing confidentiality or integrity or availability with your cryptographic mechanisms, this is something that we've got to figure out. But I think that it should be safe to say that for now, it's going to be a lot of trial and error. If we allow the space for that and the space for the failure, I think it's a better path for the future.
Great, thanks. I'd like to ask about QRC. Why are some companies spearheading QRC before NIST has concluded its activities? Is it to protect their data and communications and clients from risk, or is it because of customer demand, or is it just simply to show technological leadership? I'm curious about this. I'm not sure who I'm going to put this one to first. Matt, Brian, would you give?
Sure. So I think you're seeing industry take a forward-looking approach to deploying quantum-resistant cryptography, because we look at the timelines of how long it takes us to migrate systems based on our past experience, and when we expect a quantum computer to potentially show up that's big enough to threaten our current systems. When I started our project at Microsoft was back in early 2015, and we have a quantum computing team that's trying to build a quantum computer at Microsoft. And in 2015, I asked them for their best guess as to when we'd see what we call a cryptographically relevant quantum computer. That is, one that's big enough to threaten what we do today with RSA and elliptic curve. And their guess then was 2030, roughly, so 15 years. Well, if you do a work back plan and say, I have to upgrade the internet by 2030 and everything connected to it, 15 years is not a lot of time. And we in industry have had experience in the past 20 some odd years. We've done 4 major cryptographic algorithm migrations. They've all been simpler than this one that's coming for post-quantum. And they've all taken us a long amount of time. So I think what you're seeing is industry starting work early because of our experience with how long simpler past transitions have taken us. And we're just trying to get a jump on things, knowing that we have to be deployed before that quantum computer that is big enough actually materializes.
So generally, we're starting earlier because of the reasons you've articulated. Is anybody seeing from their experience certain industry verticals, whether that be financial sector or even government, looking to adopt QRC ahead of others? Anybody seeing any difference in the types of industry that's going this way, Panos?
So for my personal anecdotal evidence, it's not like I've done a statistical study, but we have seen interest, at least here from our customers, from governments in the US and Europe, and we've seen interest from financials, oil and gas, and a little bit of service providers. And if I can speculate the reasons why we see these verticals, I think it could be basically because some of these organizations come up with requirements for countries or for industries, so they want to be informed in this space. It could be because some of these organizations are heavily regulated, so they see the quantum threat as affecting them in the future, so they want to be prepared. And I think sometimes it's also big organizations that have groups that deal with emerging technologies or new stuff that are coming out, and they want to be prepared. So sometimes they just want to hear and they ask questions, right? I don't think we have lost an RFP because of demands, post-quantum demands, but I expect this picking up, and I expect pressure to all of these companies to have solutions in the future, right? That's my experience so far from actual customers.
Yeah, no, I wanted to say that this is pretty much in line. The first place where we saw it as well was with intelligence agencies who were very clearly trying to also do standardization for government communication. And then afterwards, we were very interested as service providers to how could we actually provide this as a service to those customers that were asking for it, and understanding that there was a little margin for error, so that we would have to compound it with other things and other, like for example, QKD. And then also we started working with the banking industry because they have a very low risk tolerance, like to start early and also have the budget to pay for it.
How about we move on and we go back to this early adoption theme. What about hybrid solutions? Do we think that hybrid solutions are necessary or prudent today for use early adoption? Anyone got any views about the hybrid approach?
Hybrid refers mostly to a combination of a classical key agreement scheme like Diffie-Hellman and a post-quantum scheme like Kyber. But I think it also can apply to two post-quantum schemes or a post-quantum scheme and QKD. So, I mean, we've seen a lot of systems fail in the past, both in design and implementation. So there's inherent value in protecting against a single failure. We think for our most sensitive communication channels, it makes sense to use a hybrid scheme, whether that's a classical and post-quantum, two post-quantum schemes, or a QKD scheme. I think NIST and the community is moving as quickly as possible, and we don't think we can move any faster in a prudent fashion. So I do like hybrid for some interim period. I'm not sure I have like a clear milestone like 10 million research hours or 10,000 analysis papers that say, okay, I think we have the assurances that warrant a single scheme for the future. But you still have implementation errors. And so having some separation there is useful for redundancy.
Thanks, Matt. Jay, did you want to comment on that?
No, I think that's actually really valuable. I think building in a hybrid solution with that combination for resilience is actually the right way to go.
Thanks. Brian, are you indicated you wanted to comment on that earlier. Do you want to come in with Matt having said what he said? Do you want to respond?
So thanks. I also tend to interpret hybrid in terms of a combination of a classical scheme plus a post-quantum scheme, not a PQ plus a QKD. So looking at classical plus post-quantum, the reason we're interested in deploying, and we've done experiments so far deploying hybrids, is basically because of Jaya's earlier point about algorithms needing bake time, that you gain confidence in algorithms based on the amount of time and analysis. Matt raised this point too. And all of the schemes that are being evaluated by NIST right now that are in round 3, frankly, none of them have gotten, even though some of them have been around, are based on problems that have been around for a while, none of them have gotten the level of analysis and scrutiny from the cryptanalytic community that RS analytic curve and their underlying problems have. So one of the reasons to look at moving to hybrid schemes as a first step is because it allows us to add in some quantum resistance without giving up any of the classical strength that we have come to depend upon from our classical algorithms. And then over time, you can deprecate the classical algorithms as we gain more confidence in the classical computing resistance of the post-quantum schemes. You got to always factor in the deprecation time, and that can take you a while. Just turning an algorithm off takes a while too.
Panos.
And also don't forget FIPS, right? So until we have a post-quantum FIPS approved algorithm, the use cases that have to be FIPS approved, they'll have to do hybrid. So they can use a FIPS approved classical algorithm.
Well, look, let's touch on QKD briefly then. Anybody got any views on what role QKD may play in post-quantum cryptography, or anybody prototyping or done some work with it yet?
Yeah, so it was one, I have to say, I'm a chief information security officer, and we tend to be opportunists, using whatever's available when it's available to accomplish the thing. So that approach for us at KPN meant that first and foremost, we would kind of follow the advice of increasing the key length of all of the current algorithms we used in the network, and then, because that was something we could do right away, to buy ourselves some time. And then we would look at QKD for very specific use cases where it made sense to apply on our network, because again, this was technology that was simply available. And we could just try it out, put it in the data center, see what it looked like, try to figure out how it worked. And then we are very much invested in starting early with post-quantum algorithms, because again, we want to understand how it works and what's the impact on bandwidth, on computation resources, on optimizing for the applications that we use. So really, I really think that that's kind of the way that pragmatically you're going to have to go. So for us, the use case is that, and I agree with the hybridization in all the ways that we talked about, but an approach where you have a link that is already post-quantum secure and then implementing quantum algorithms on top of that, that's something that I think gives our customers a lot of confidence.
Thanks. And Matt?
So we've really just been monitoring QKD at this point. We did analyze how a QKD solution would work for our infrastructure. They seem to have a place. I mean, they have a place in link encryption. Today, we can see on AWS it's broken up into regions. Regions are made of availability zones. The availability zones are all typically within a single area, less than 100 kilometers apart, that lends itself well to a QKD solution. In addition, we have AWS Ground Station, which is a fully managed service that lets you control satellite communications. And finally, we announced Project Kuiper, which is an initiative to launch low orbit satellites to provide low latency internet connections. So it's possible to sort of assemble a fiber-based QKD network within a region and network these things through space, satellite to ground. But the cost benefit of doing that does not seem to justify the value of sort of information security over computational security. And the attitudes from our customers, we just haven't heard that demand that would move us towards providing that information theoretic security versus the computational security that we have been using for decades.
Well, we're going to open this up to questions from our audience very soon, but one more quick question from myself. The bandwidth and performance of the proposed post-quantum crypto system varies a bit. I'm curious as to whether we define a segmentation for our products and our customer needs, and whether that's a factor at this stage. Jaya, have you got any thoughts about this yet?
To try to answer the question that you're asking, I think there are customers that really want optimized bandwidth, but there's something to be said for ubiquity. So whatever solution we finally wind up going with, depending on the application, I think the customers that we've spoken to in the banking sector and also in government, they're really looking for things that are going to be applied everywhere, if you will. So they don't want too much customization just for them. So they're really like, I have to go back to the QKD question for a moment, because I was thinking about the fact that when we were doing this at KPN, we were also working together with the University of Delft to try to examine solutions for achieving that ubiquity. Can we actually do this on a link encryption at scale where we would actually be able to provide a quantum internet solution and not just a node to node type connectivity? And it's the same applicability that we are talking about when we're looking at particular applications that we want to provide to customers. So the banking customers, as well as the government customers, they don't want to have unique algorithms. They don't want to have proprietary applications. They want to be able to have something that would be applicable to other sectors and other verticals.
Great, thanks for that. Look, there's a lot of areas we want to cover. We still haven't covered everything we want to, but we're going to pause our discussion here because we now want to hear from our audience. So for now, everyone, thank you very much, and we'll speak to you again very soon. Look, if you haven't already done so, then now is the time to send in your questions for our panelists. In a few moments, we'll be back with our live Q&A session, and we'll resume our discussion on the challenges of moving to quantum-safe technologies. So please use the form here on the website, send us your questions, and we promise to get through as many of them as we can. We'll be right back after this short break.